Okay, good afternoon, everyone. Thank you very much. So first, I would like to thank the organizers for giving me this wonderful opportunity to come and speak on this topic. And yeah, I really look forward to, and I'm very grateful to see, it's very nice to see such young, energetic people. Okay, so one thing I would request you is, so I have a very disorganized set of slides, okay? So please ignore the slides, okay? So that is the first thing I will request you. So, and the second thing I will request you is, if at some point in time you have a question, please stop me, okay? Please stop me and ask. So I really like things to be interactive. And there are so what I'm going to talk about in this talk is some of the works that I have done, some of the projects that I along with my colleagues have worked on, and so that is what I will be talking about. So please ignore some of the details which are may not be very relevant to a general audience. Okay, so. So what I would request you is to take away. So I will talk about a few real world problems. So instead of going into a general what machine learning is and things like that, I will talk about a few real world problems which have a certain research challenges. Okay, and how we can solve those. One of the ways of solving those problems. Okay, so. So if not anything, please take away the problem. Okay, so what are the problems people are trying to solve? Okay, and then maybe take away some of the techniques that can be used to solve those problems, and yeah. So okay. So with that, I will start with the obligatory slide on big data, which is basically large amount of data. So there are 3 V's, sometimes people call 4 V's. Okay, I need not repeat this. I think already you have heard a lot about these things from very eminent experts. So even this you have heard a lot. I would just want to focus. So just to at the cost of repeating myself, okay, or rather repeating. So why is big data so important now? Because there are many sources. So one source is like social media. In general, it is called user-generated content. So tweets, news articles on the internet, the emails that you send, the browsing, the Facebook post, everything, right? All these things. Okay. So most of my works are in that domain. Okay, so this is one big bunch of source of big data. So that is a very important source of big data. I will not talk about some of the other things, but there are so for example GPS coordinates. So the other very important source of big data is this sensor data. Okay, so there are various kinds of sensors which have now come. Okay, so like RFID sensor, this GPS sensor. Okay, in some sense you can think of videos or images captured by your camera. So those are also some kind of sensors. So these are becoming sources of the big data. So that is why big data is so important. Okay, and why is machine learning important? So again, just to repeat. Machine learning helps you make sense of the data, helps you to perform tasks, make decisions, build products which are based on the data, right? So that is the job of machine learning, if I call it broadly. So I mean. Obvious or if a very naive way of thinking about it is, since machine learning depends so much on data, if you have big data or if you have different sources of data, probably machine learning will be more effective, and which is what is happening every day. Okay, so that is why we are looking at machine learning on big data. Okay, so so that is the broad theme. With that, I will just I will start on the first problem, which is the named entity disambiguation problem. So this is joint work with my students Rijula and Shushmija, and Professor Anirban Dasgupta and Professor Soumen Chakraborty of IIT Bombay. Okay, so so what is the problem of named entity disambiguation? So have any of you seen something like this, that when you browse a web page, sometimes some texts will come underlined, not the linked, they are not hyperlinked, but still they will come underlined. Okay, and if you hover your mouse over it, some information will crop up. Have you seen? Sometimes it comes. So that information is, let's say, extracted from somewhere, let's say Wikipedia. Okay, so let's say that information is extracted from Wikipedia. So the question is, how do you say which Wikipedia article should you extract information from given the text? Can you do it automatically? Okay, so this is one task. Okay, so this is the task of named entity disambiguation. Okay, now what will be the normal procedure? So the task is that you are given the text, okay, and you have to sort of figure out which of these are talking about certain entities in Wikipedia. So I am just refining this term entity. Okay, entity is something which has a Wikipedia page. Okay, let's say a simple thing. Okay, so how do you determine whether something is an entity? So let's say I give you a piece of text, right? So how do you determine whether something is an entity and which entity is it? Okay. So what is the simplest solution? The simplest solution is you just take that string, you do some kind of string processing. There are so many text analytics tools. Okay, and then you do stemming, normalization, all these things, and then you try and match with, let's say, the title of the Wikipedia page. Okay, something like that. Okay, and then you say this is related to this. Okay, so that does not always work. So there are many cases. One case in point is this Michael Jordan. Okay, so there are two Michael Jordan. One is a very famous professor at Berkeley, and the other is a very probably more famous basketball player. Okay, so and both are Michael Jordan, and so if you match the string Michael Jordan, then two Wikipedia articles can come up. And so what will you do? Okay, so what is the other cue that you have that will help you choose between these two? Okay, so the other cue is the words which appear nearby this Michael Jordan. Okay, so this Michael Jordan is sometimes called the mention or the alias, and the words around wherever Michael Jordan is appearing is called context. Okay, so we have the context, we have the entity, and we have the mention or the alias. Okay, and now our problem is to actually disambiguate the entity which corresponds to this mention in this context. Okay, so that is our problem. Okay, okay. So those who, so I'm kind of assuming most of you are familiar with the basic machine learning stuff. Okay, so the simple solution will be, it's a classification problem, right? So it's a classification problem that you have the features which are there in the context, okay, and also in the probably the mention, and then you want to classify, and you have various classes. Okay, each entity is one class, and you want to classify the mention and context into entities, and that is one approach, and that's a good approach. Okay, so that's kind of our baseline approach. Okay, one thing here is, if you try to do this, you get into something called representations for entities. Okay, so think of it something like this, that you get a large high dimensional feature vector from the mention somehow. Okay, some deep learning technique, if you have heard about the term, but otherwise it's fine. So, and then you just take a dot product of this large mention vector with the entity vector. Okay, so if there are two entities, let's say Michael Jordan the statistician and Michael Jordan the basketball player, okay, so then you take the dot product, and this dot product is your score. Okay, score of that entity. Okay, so whichever entity scores highest is the correct entity. Okay, so that is the disambiguation mechanism. Okay, now, and there are certain parameters. So there are certain parameters that would come if you go this route. Okay. Okay. Now, what is the problem with this approach? Okay. So the problem with this approach is, in practice, what happens is that you have for certain mentions, so you will train this on every mention. Okay. Now, how will you get the training data? So the training data you will get is wherever in Wikipedia you have a link to that particular entity. Okay, you will take the context around that and take that as a positive example, and something else as a negative example. So same word, same mention appears, but the link is to some other entity. Then that's a negative example. Okay. Now, certain mentions will have very few links. Maybe they were linked to from by 2 or 3 Wikipedia articles. Okay, so 2 or 3 positive examples are there for this kind of mentions. Okay, but the classifier that you learn can be more general. Okay, so there are many tasks, right? So there is one task of disambiguating Michael Jordan. There is another task of disambiguating Apple. So Apple is another mention. Okay, Apple can be the fruit or the company. Okay, there can be the mention Jordan. There can be the so many mentions can be there. Okay, many of the rules of disambiguation are very can be common. So for example, so if nearby, let's say the word Jordan, if nearby there is water or some such thing, okay, then it's the Jordan River. If nearby it is like capital and president and all these things, then it is probably talking about the Jordan country. So these things, some of the rules will be common across this thing. Okay, so the information that you are throwing away is, in the first approach, is that you are not borrowing between mentions. Okay, so you are not borrowing information from one mention to the other mention. Okay, so that is the domain of multitask learning. Okay, so multitask learning takes many such classification. I mean, in this case, classification tasks. It could be other tasks also, and then it tries to jointly learn a model for them. Okay, so what is the multitask learning model? You can think of it as 2 classifiers. Okay, so the first classifier learns a common representation. So in this case, the whole classifier I am calling it GU, and the first classifier is the first layer. So it's, you can think of it as a 2-layer neural network. Okay, or a function of a function, composition of functions. Okay, where the first layer is learning the representation of the mention, and second layer, which is specific to the task, okay, is doing the classification. Okay, so earlier you were learning only one such function, now you are learning 2 functions, or one function and then on top of the second function. Okay, so the first function captures the common characteristics across the task. So this is existing work in multitask learning. Okay, so so the problem with this, so now can you, so what is the problem? So we found, so this is a very well celebrated approach in machine learning now, okay? But we found a problem with this approach for this particular problem, okay? At least for this particular problem, this approach also has a problem, and that is the problem that we solved. Now, what is this problem that we found, okay? So the problem is that you see this initial layer H, okay, it is not dependent on the task, okay. So only the layer which has subscript U is dependent on the task. So the final layer is dependent on the task. Task means that mention, okay. So the mention that you want to classify or disambiguate, okay. So the first layer is generic, okay. And what that means, so now just to give you a scale of the problem, something like there will be close to 1 million entities, okay, in Wikipedia, okay. And yeah, like you will have like about 50 GB of data, okay. And this is a really large scale problem, okay. And in order to capture the representation, all the nooks and crannies or all the aspects of all those mentions, okay, like if so in case of Apple, in order to disambiguate, you have to check whether, you know, there is a laptop or MacBook or something in the context. If it is there, then we are talking about the company, otherwise we are probably talking about the fruit, okay. Now in case of Michael Jordan, there is something else, okay. So you can understand the complexity of the representation that you want to construct in the first layer, because this representation is common, okay. So you want to extract all these features from the mention context, okay. So that is a really huge task, and the way that manifests in practice is that you generally need a very large dimension of hidden layer, okay. So very large dimension of the first layer, okay. So in order to get even some simple very simple performance, you need to get a very large dimension, and that causes all kinds of problems for training, for scalability, for everything, okay. So we came up with this architecture called task specific representation learning, okay. So what is the task specific representation learning? The switch is very simple. The switch is the first layer is now dependent on the mention, okay. So it is like the representation is specific to the task, okay, and then there is a common classifier, okay. So so now so one basic question comes is how do you get this common classifier, because you know your set of labels is different for different tasks. For Michael Jordan, it is the statistician and the, you know, the basketball player. For Apple, it is the company and the this thing. So you don't have a common set of labels. So how do you have a common you know, final layer? And we get this common final layer by learning a common entity representation. So the final layer is this dot product between the task specific mention representation and the common entity representation, okay. And this is how you classify the, you do the final classification, okay. And this helps a lot, okay. This not only reduces the model complexity or the number of parameters, increases the speed of training, but also it improves the performance, okay. It improves the performance because actually if you learn a common representation, many a times it get confused, okay. So your next level classifier may get confused, but if you learn a context sensitive specification, you, so come to think of it, for telling whether a particular mention of apple is company or fruit, you only need like whether a certain words, right, like just whether laptop, maybe cable, all these things. You don't need to know everything about all Apple products. You don't need to capture all those, right? All those will confuse the classifier. Okay, so this is what we see, and this is like a kind of the graphical representation of this. And so the first layer is so the first layer is TSRL, the bottom one is TSRL, and the top one is multitask representation learning, which is the existing framework. And I will skip the task clustering. Actually, we can further we can actually break the problem into sub problems because we take this approach. By the way, can I ask why not add task specific layer in both layers? So I said so many things, nobody asked me this question. Why not also add FU? Because then it will be same as per alias classifier. Because the parameters are specific to the task, and then there is no difference. It's just a two-layer network which is per alias. There is no dependency among the parameters. And if there is no dependency among the parameters, you cannot borrow from one task to the other. Okay, so in order to borrow from one task to the other, you have to have common parameters. Okay. Okay. So with this, so kind of the last line is our best attempt, where we include we use the task specific representation learning, and we also include the Wikipedia pages of gold entities into the training set, and that gives kind of the best performance. Okay. Otherwise, just with gold mentions, we get 88% micro average accuracy. So you need not go into the details of the number, but the key idea is the key idea clear. Okay. So how many people have I lost already? Okay. Okay. So can you tell me now, will TSRL do better on mentions which have low amount of training data, or worse on mentions which have low amount of training data? So you remember the whole idea of going to multitask learning was because certain mentions don't have enough training data. Okay, so we are getting very, very bad accuracy on those mentions. Okay, so what will this TSRL do compared to the existing multitask representation learning framework? So actually, it turns out that so that is so this is with respect to sorry. So this is okay. So this is the performance of different classifiers with respect to the bins of entities which have high training data versus low training data. Okay, and we see that actually we do well. The TSRL does well for entities which have high amount of training data, but it also does well for entities which have not so high amount of training data, like the so the left bin is the highest training data, then the second bin, then the third bin, and so on and so forth. Okay, so so the method also does better on bins which have low amount of training data. Okay, and these are some anecdotal examples. So for example, we have this so this mentioned Brazil and another mentioned Brazilian. Okay, and Brazil has 95,000 training instances. Brazilian only has 1,180 training instances, and If you see per mention classifier does very poorly on Brazilian as expected, but then TSRL does pretty well. Okay. So, okay. So any questions? I will not repeat the conclusion. Any question about this? Next slide.
Before slide of
this one.
Brazil and Brasilia, if we use lemmatization and mark these two things,
Yeah. So probably no, but then
because if we use lemmatization, then Brazilian becomes well.
okay. So here, see the yeah, okay. So in case of Brazilian, probably it might become Brazil. But what about John Gorst, for example? John Gorst versus Gorst, or Germany versus German.
German and Germany will be different, but in case of lemmatization, Brazilian and
I don't know if Brazilian becomes Brazil though. No.
it's not possible, but if we use lemmatization, then Brazilian.
Okay, probably Brazilian will be covered. Yeah, I'm not sure, but yeah.
And Australian, I think Australian also converted.
I'm not so sure actually, but anyway. So yeah, but there are many other cases, as I said. So the problem is general, like the problem is not that of how you can match the surface forms better and merge problems, right? Because yeah, you can understand that at a conceptual level, it is not the problem of whether the surface forms can be somehow captured and but it is a multitask learning, because these are two different tasks, but they are related tasks. Okay. Okay. So okay. So we go to the next. So this is work on modeling opinion dynamics. Okay, with Abir De, Isabel Valera, Professor Nilay Ganguly, myself, and Manuel Gomez Rodriguez. Okay, so let me give you the idea of the second problem. Okay, so you have seen this Twitter poll kind of thing. Have you seen these Twitter polls? So people they express over Twitter their sentiments for a particular political party versus another political party, and then your task is to automatically say so the first task is automatically just counting how many people are saying yes for like A, and how many people are saying yes for B, and how many people are undecided or somewhere in the middle, right? So this is the first task. The second task could be I don't want to say what is it today. Okay, so I can say something about the current count. Can I say what will happen 2 days or 3 days or 5 days from now? Or in other words, what is the trend? How are things evolving? Okay, so can I predict opinion? So can I model the dynamics of opinion? Okay, so that is the problem. Okay, so so there are so politics is one application, product rating is another application. You want to predict sales or something. Okay, so and these things I think you can probably understand that you have basically two sources of data. One is that you have a fine-grained opinion. So users are expressing their opinions, fine-grained opinions on the various platforms. So you can measure those at a very cheap cost. Okay, and second is you have the network connections. Okay, so you know which user is listening to which other user, and so basically which user is getting opinions from which other user. So that information also you have. Okay. So what does it, so what is the simplest kind of model that you would think, okay? So the simplest, so this is like a general dynamics model, so it's a discrete time dynamics model. So at time k, if you have opinions of all the users, so let's say you have taken a set of 500 users or something like that, and you are studying how their opinion is varying, and now you have at time k all their opinions, okay, and you want to predict at time k plus 1 how their opinions will be, okay. What is a good form? So another thing is that this is a question of convention. So in our work, the convention is that 0 is kind of the neutral opinion. So there are two polarities. 0 is yes or no, good or bad kind of thing, okay, and 0 is the neutral opinion, okay. So positive is, let's say, good, negative is bad, and they're kind of unbounded. So we don't really care whether they are between certain values, but you can also have them, okay. But 0 is the neutral one, so that is important, okay. Okay, so if this is the case, okay, one way of modeling dynamics, which is also people have, some people, so there are many opinion dynamics models, by the way, in the literature, okay. So, but one way of doing it is what is called the linear model. So basically what we do is we have one parameter for every edge in the network, okay. So for every edge in the network, we have one parameter which models the influence of ith user over jth user. So aij is, sorry, in this case the jth user over ith user. So and then you sum over all users from which the user I receives the opinions, okay, and then the next opinion is predicted as their product over the influence and the opinion of that user j in the previous instant of time. So the model is clear. So if I am trying to form my opinion now, I take the opinions of all my friends and I multiply each of their opinions by the amount of influence they have on me, and then I add that up. Okay, so that is my model, and if that is the case, then you can do some standard machine learning stuff. Okay, so I will not go into the detail of mathematics here, but you can see that this the first is basically your update equation. It's a set of dynamics, so it's the update equation, and then given a ground truth data, you can actually learn the parameters. Okay, so you can so what are the unknowns? The unknowns are the influences, right? So how much influence does my friend have over me? Okay. So that is what will determine the dynamics, okay, and we can, and it's a, you can, so the simplest model that we proposed is like a least square model, and you can do many different kind of predictive models, okay. So this is one solution, and we tested this over some data, and it gives decent results. So it gives good. So there are many other models, okay, which don't learn the influences. Rather, they propose something. So they propose that if my opinion is similar to your opinion, you will have more influence on me. So this is called homophily, okay, or sometimes so these kind of things, okay. So sometimes I will just randomly copy my friend's opinion, okay. So that is called the voter model, okay. So these kind of things, okay. Aij is not symmetric, yes. So for most general cases, Aij will not be symmetric, okay. Now what is, so this is our first model, okay. So what is the problem with this model? So I always tell something and then there is a problem with that. Okay, so what is the problem with this model?
If the opinion varies 0 to 1, that is fuzzy.
No, think like opinion is from -1 to 1, let's say. For simplicity, think that we have renormalized the opinions from -1 to 1. Though that is not necessary, but think like it is -1 to 1 and 0 is the neutral point. But we can always renormalize, no? We can always rescale it to -1 to 1. Okay, so the problem is a little subtle. Okay, I will tell you what the problem is. The problem is the following. Okay, so the problem is that it sort of unifies two things. One is when you form your opinion, and two is when you express your opinion. It is this one and the same in this model. Can you see? So for example, I will. So if according to this model, okay, if let's say one of my friends who has a high, so let's say there are two friends of mine, both have equal amount of influence. One has expressed an opinion 5 times 5 months back, okay, and the other has expressed an opinion like last minute, okay. Both these, so this guy will this guy's opinion will have a higher influence of me because he expressed it 5 times, okay. So but that is not reality, right? That is not reality, okay. So we keep thinking about things, and only every now and then we express our opinions, okay. So or just because somebody is repeating it 5 times doesn't mean I take that 5 times into account, right? So I do a decay, okay. So that is the problem with this model, okay. And in order to capture this, we proposed what is called the continuous time opinion dynamics model, okay. So I will just I have only 5 minutes left, okay. So then this will be my last this thing, okay. So the model is the following, okay. So the model is okay. So the model is something like this, that we model two things, okay. So one we called the informational influence, okay. So the opinion value of a friend, okay, affects my opinion value. The other is the temporal influence, okay. Temporal influence means if somebody is posting an opinion, okay, the fact that he is posting an opinion now affects whether I will post an opinion or not, okay. It may or may not affect my opinion value, okay. So the time will affect, but in a different way, okay. So these two are decoupled, okay. So the informational influence and the temporal influence are decoupled. This is the first thing, property of our model. The second property is that we have two different random variables, one for the latent opinion and one for the expressed opinion. And the expressed opinion is basically a sample from the latent opinion, which is a continuous, which is a stochastic process basically, which is a continuous time random variable, okay. So okay, so what is the so first is how do we, so two things we have to model. First, we have to model the rate or the propensity of a user posting their opinions, okay, and that is modeled by this rate function called lambda. So this is a standard technique in like point process modeling, where or event modeling, where you model the rate of events as the expectation of basically rate of change of the counts, okay. So this is like a counting process, okay. So this is one, okay, and the rate depends on against the same influence kind of score, and now this time multiplied by a memory kernel, okay, or like a temporal kernel. So if, for example, this could be, the kernel could be like a exponential decay kernel. So if you have, or if my friend has proposed something very much in the past, then even if the influence of that is high, the kernel may decay it. Okay, so so then it is sum over the same thing, but yeah, and a similar thing for the latent opinion. So X, so on the left hand side is the user's latent opinion. Latent opinion means what he or she is thinking in the head, not expressing. Okay, so this is not what we are measuring. Okay, so and then we have a certain sentiment, we call it the sentiment, which is the measured opinion, okay, and which is a sample from the latent opinion, okay, and you can have different kind of measurements like discrete or continuous measurements, okay. So we show some mathematical properties. So we can, for example, tell when this system will actually will, let's say, achieve a consensus, or will there be a convergence of opinion, first of all. So if I, given a system, if I let the dynamics run, will there be a convergence of opinion, okay? And also we can estimate the parameters of this model. So there are two types of parameters. One is the temporal influence, and one is the informational influence, okay? And this model does pretty well, okay? So for example, so without going into the details, you can see that this till about, I think, 3rd May or something is the training time. So this vertical bar is the training time, okay? And after that is the time when we are actually predicting, and the green line or the black line are the okay. So yeah. So this bar is the time till which we know the opinions, and after this we are predicting. So the purple one is the actual opinion, and this green line, black line, all these are predicted, where this t is basically the amount of time we predict in the future, okay? So the amount of time we predict in the future, okay? So, and we see that we perform well, okay? So this is okay. So very quickly I will just describe an extension to this work, okay? Can you tell what problem is there with this work? So there is a problem with this work. Probably there are many problems with this work, but there is at least one problem with this work. And the problem is that what we assume is that the dynamics is always endogenous, okay? So when we say always endogenous, we mean that whatever data we are observing, okay, people in that subnetwork are getting influence from each other, okay, and that is how the dynamics is going, okay. But that is not the case in reality, right? So in reality, people read, so some people read, news, some people watch TV, okay, and they get some more opinions, and then they post those opinions. So those opinions are not formed from previously expressed opinion on that data stream, okay. Suppose I am observing Twitter, okay, those so it's not going to appear in that data stream, okay. So these are called exogenous opinions, okay. So any stream will have two types of opinions. One is endogenous opinions, which are resultant of the dynamics in that stream, okay. So it is because somebody has expressed some opinion beforehand in that stream, and then people have somebody has got an influence from those opinions, and that is why they are posting that opinion. or they could have read it elsewhere. Okay? And this task is about how to demarcate these two. Okay? So, so very briefly I will just mention, so one simple idea could be that you have the tweet, so you just take the contents. Okay, so if the contents are similar, then they are if the content matches the content of one of the previous tweets, you have the same thing, otherwise you have different. Okay, what is the problem with that? The problem is that even if the content is same, it could be exogenous. Okay, so it could be about the same topic, but somebody could have gotten the opinion on on a totally different thing. So example is, New York Times hints at a new trade war, and a timely article in New York Times. Okay, so so the content wise there is a huge amount of similarity, but clearly you can see that they are getting their information from different sources. Okay, so it doesn't say that given the first one, the second one is endogenous. Okay.
And also the messages can be differently interpreted subjectively, like maybe a satire or something, even though the words might be similar.
Yeah.
Exactly opposite message.
Yeah. So we can discuss this, but satire is even now very difficult to handle. Typically, we don't. It's very difficult to handle satire, and yeah. So we can discuss those. Okay, but okay. So what we are doing is the following. Okay, so what is a good way of demarcating the two? Okay, so any suggestions? So now you have seen the opinion dynamics model. What could be a good way of demarcating the two? So one way, so there can be many ways actually. So one way which we found works pretty well is we take these parameters. So we take the parameters of this opinion dynamics model, and we try to estimate the variance of the parameters. Okay, so variance of the parameters are like something like how how much. So if I perturb the training data set a little bit, okay, how much the parameters would change. Okay, and then if I am able to reduce the variance, so is the idea the variance of the parameter is fine. So given any training data set, I can, using whatever algorithms I have just described, okay, I can estimate the parameters of the model. Okay, and when I estimate the parameters of the model, if I change the data set, the estimated parameters would change. Okay, and the question is, how much would this change? Okay, so if they change too much, because I have changed the data set a little bit, okay, that probably means that the parameters are not very robust. Okay, so if we are trying to model both endogenous and exogenous opinions, okay, my parameters would not be very robust. Okay, but if I only include the endogenous opinions in the training data set, okay, my parameter estimation will be pretty robust. Okay, so in other words, even though I am reducing, so normally in machine learning, when you reduce the training data set size, the variance of the learned parameters increases because you are less certain about the trained parameters, right? Here, we are trying to actually increase the variance of the parameters by reducing, so selecting a subset of the examples which are the endogenous examples. Okay, so that is the broad idea. It turns out that you cannot solve it exactly, but you can have. So we show that it is submodular. So we take this function actually. So A is the covariance matrix, and we take the trace log function of this, and you can show that basically this is submodular, and you can use a greedy approach to select the messages which are endogenous, and it gives an approximation guarantee. Okay, and yeah, so you see this is the same thing. So it is the same model, slant is the previous model, okay, and then we are sort of doing this cherry pick, which is selecting the endogenous opinion. On the test set we have not selected anything, but still we are able to reduce the predicted. So you can see that we are really selecting the endogenous opinions. Okay. And then this is another interesting graph where this is like, so we have to specify a percentage, like what percentage of the opinions do you think is endogenous or exogenous, and we see that below a certain percent the error increases, above a certain percent the error increases. So there is a sweet spot somewhere between 70 to 90%. For it will of course be specific to the data set, but for that data set, that is the percentage of, so there is kind of a ground truth about the percentage of endogenous opinions, which is somewhere between 70 to 90% are endogenous. Okay. With this I will stop. So I think can I, yeah, oh, okay, okay, thank you.